All right, hey guys. I know the CK12 assignments have been a little tricky, so I'm going to send you guys this screencast. I'm going to do a little bit of notes on free fall, solve an example problem, maybe two. Um, Hopefully that'll give you guys a base to solve those. I know those are tricky. Try your best. Try to get as much as you can out of them. They're probably a little harder than what we would have done if we were in class, which is why I'll help you guys with this. All right, so free fall is what we're looking at now. Your CK12 calls it like acceleration under gravity or something. I don't know what it's called, but free fall is when only the force of gravity is acting on an object. So anything thrown like this, dropped, the first example we'll do is an object dropped. But anything that's only acted on by the force of gravity is in free fall. So it could be like this. We won't do any two-dimensional motion, but it could be thrown up like this, dropped. It doesn't have to just be falling to be in free fall. On Earth, okay, this is on Earth right here. The acceleration due to gravity of any object, regardless of its mass, is 9.8 meters per second squared down, which means anything that's falling is getting 9.8 meters per second faster every second that it's in the air. If it's traveling upwards, then it's still changing its speed by 9.8 meters per second each second, but if it's going up, it's going slower because it's getting pulled down. We're going to talk about this down here, why mass doesn't matter, but we'll talk about that in a second. By the way, if you guys can't read any of this on this video, or if it's tough to see some of the colors, I'm going to screenshot this and put it, or I'm going to doc scan this and post it online too, so you can follow along with this on your screen as I'm doing the video. All right, so let's quickly do this example problem that I wrote here. Just pick some random numbers, and then we'll do another harder one, and I'll do one from your problem set online. All right, so if an object is dropped from 1.6 meters high, what's the time that it'll be falling? So for all of these, we have to write down, the first step is always draw the problem, and then the second step is going to be write down all the givens. For all of these, we're going to know three numbers. Now, what's tricky about free fall is that this problem only has one number. So if you were like, okay, we're reading the problem, maybe we underline, that's a good way to go about these. Underline the number, 1.6 meters high. But that's the only number they give us, which makes these kind of tricky. So, object dropped from 1.6 meters high, what's the time it takes to fall? So, first thing I do is any number that's actually in the problem, I write that down. Now, any number for one-dimensional motion is going to fall into one of these five categories, unless it's average velocity too. But anything that's speeding up or slowing down, like in free fall, is going to be one of these five numbers. The number is either going to give us how far it went, the time it took, its initial speed, its final speed, or its acceleration. These can be speed or velocity. Technically, they're velocity, but if something's only traveling in one direction, we can just call it speed. It's fine. All right, so this 1.6 meters, and the units are a really good hint to tell us which of these it gives us. The object is dropped from 1.6 meters high, which means as it goes from up here, 1.6 meters up, down, and hits the ground, it has traveled 1.6 meters. So that's giving us displacement. Now, I always like to make down, anything pointing down is negative. Okay, so I'm going to write this as negative 1.6 meters. It probably won't change our answer. We just might need to get rid of the negative sign. We'd end up with a time of negative. We can't have a time of negative, so we'll just get rid of that. But the reason is we have to have anything that's pointing down, like this or this, is going to be negative. Now we run into kind of a dead end here, or at least a fork in the road. The problem doesn't give us any more numbers. Now, one thing it does give us is this object was just dropped. Usually it will write dropped from rest if it wants to be clear. know it's hard to see that, but if it's dropped, that means the starting speed is just 0. It's not moving to start, and then you let go. So this will be 0 meters per second. The initial velocity. That's going to be 0 a lot of times. Not every time, but a lot. Something starts from rest. Anytime you see the words from rest, that means the initial speed or initial velocity is 0. Okay, so we're still only at 2 things that they give us. We need at least 3. In all of these, any equation that we can use, it's going to have 4 variables in it, so we need to know 3 of them so we can solve for the 4th. The last thing we know in any free fall problem, anything that's only acted on by gravity, is that the acceleration is 9.8 meters per second squared down. So for acceleration in all of these, we can write negative 9.8 meters per second squared. So that, even though the problem only gave us 1 number in the problem, we really know 3 things. So that's going to make these problems a little tricky. But now that we know that, the next step, the 3rd step, is figure out what it's actually asking for. It's asking for the time. So this is going to be, I usually write a question mark. This is going to be what we're looking for. There's always going to be one, the 5th one, where we just don't need at all. All right, so now this is that step, these steps right here to get these givens. This is actually most of the physics in these problems is done at this point. The rest is just picking an equation and doing the math. So if we pick an equation, the way we pick an equation is we pick an equation with these 4 variables in it. There's only one equation that has those 4 in it, and you can look on, I posted that motion study guide, or a lot of things are to give the equations for you. This equation, which we worked on last week, relates all 4 of these variables and doesn't have final velocity. We can't find, using this equation, how fast it's going when it hits the ground, but that's fine. It's not, they don't give us that number, they don't ask for it, we don't care about it. We could find it if it asked for it, but we don't need to know about it. So, now that this is sort of step 3 or 4, depending on how you count, pick an equation. Now all we do is anytime we see one of these variables, we replace it with the number we already wrote down here in the givens. This is why we do it this way, is because from here on out, there's really not much more thinking, it's just doing the math. So anytime we see change in x, we plug in negative 1.6. We don't need to keep the units. I like to put the units here, and we need it in our answer. You don't need it if it's already in the equation. Initial velocity is 0. So 0 times anything is just going to be 0. So this whole number right here is just going to be 0. Plus 1/2 times a, which is negative 9.8, times t squared. Now we have an equation with just one variable that we don't know. We can rearrange and solve for it. If we're looking for time and it's in the squared here, the last step is always the square root, okay? So we can do some steps here. We can multiply 1/2 times 9.8. This 0 doesn't matter anymore. So we get negative 1.6 equals negative 4.9 times t squared. 4.9 times t squared, we need to undo that. So we divide both sides by negative 4.9. Make sure the number that's actually next to the t squared gets canceled out. And then, so we have, what's 1.6? Divided by 4.9. This is not working. It is 0.33. 0.33 equals t squared. We're not done yet. Negative divided by a negative gives us a positive. The last step is to take the square root of both sides. So square root of 0.33 is 0.57. So we get t equals 0.57 seconds. We need the unit there. All right, so there's our example problem. Most of the work comes from figuring out what you're given and what the problem's looking for. All right, I'll talk about this later. I'm going to do your another example problem, one of the ones that was actually on your homework, or is on your homework this week, because that one gets a little tricky. It's something thrown up in the air. So I'll do that in the next video.